We just defined importance sampling and what an importance sampling estimator is. And so I guess I didn't mention here that this Q is called the proposal distribution. Proposal distribution. And in this video, we're going to take a look at draw some pictures to try to get some intuition for what makes a good choice of Q and what makes a bad choice of Q. So let's do that. Let's draw some pictures. Let's say that we have, we're maybe doing some investment or something like that. We have some loss function, L. So this F, so we want to compute the expected value of f of x. Actually, let's say that it's our reward. So maybe f of x is like our return on some investment. And we want to approximate the expected return. We're going to do an importance sampling approximation. So f is going to be our returns. And let's say that f looks something like this. So we'll do it in red, or red for returns. So on this axis here, this is x. This is all the possible values that we might observe for the random variable x. And let's say we have some particular strategy that we're evaluating, and that our returns are, maybe we get some little returns over here, something like that. And then it's going along, and I think you can imagine what's going to happen. Over here, things get super bad. This just goes down the drain. So any x's over here, we take huge losses. So this is f. And we get some modest gains over here. And now, let's say that p, the distribution from which these x's are drawn, we'll do that in purple for p, is pretty small over here. It's, you know, very small, rather small. And then it's, most of its mass, the mass of this distribution p, is over in the right-hand side. That's p. And now let's think about what Q would make good. What would make a good choice of Q? Well, let's think about the Monte Carlo estimator here. The Monte Carlo estimator is going to do something like the following. Monte Carlo, you're going to draw, you know, a bunch of samples from P, right? And you're going to get all these samples, you know, over here. Boom, 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 boom. And it's looking like, you know, you're averaging, so you're averaging this, you know, f of xi. You're taking all your samples, and f over here is, you know, it's either smaller or a little bit positive. So things are looking pretty good. You're thinking, hey, yeah, maybe this is not a bad strategy. And then, but you might not, you know, this might be such a small probability over here that it's very rare that you ever get a sample. And so you never sort of see this other region where you're taking huge losses. Maybe you get one every once in a while or something. On the other hand, what could you somehow make up for this with a good choice of Q? Well, where would you like to get samples? You'd like to get samples where it matters, right? Where it's important. Hence the name importance sampling. So you want to get samples where it really counts. And here, in this example, where it counts is in this region. It's in this region. If we're trying to approximate this expected value, the expected value is the expected value of f of x is the integral f of x, p of x. And even though p is very small over here, it's still positive. It's still, you know, not too small. I mean, it's you know, it's reasonably large enough that when you multiply it by this humongous f, then most of the expected value, most of this integral, where the value of the integral is coming from, is in this region and not over here. So this is this region is not contributing much to this integral, and this region is contributing a lot. That's the picture I'm trying to draw, at least. Whether I did it well or not, I don't know. So we would like to draw samples where it's important. So we want to weight our distribution, I don't know, maybe even bigger, something like this, our Q, to get most of our samples over here. And then maybe we want to get some samples over here, something like that. So this would be a good choice of Q. good Q. And you can start to get some intuition maybe for why a Monte Carlo estimator might not do well in certain problems, and why you can improve the the quality of your estimator by lowering its variance, by lowering its and therefore lowering its mean squared error, by adjusting to a different distribution and using importance sampling. Okay, so that's one example. Let's draw another example. This is the ideal situation where you can actually draw a good Q, and your original P was doing very badly. But let's draw a situation now where maybe you choose a bad, where things might go wrong. Maybe I'll do it down here. So again, we have X. And now let's suppose that F is, it's, let's do it in red. It's doing its thing over here. And then let's say it gets pretty big over in this region. Boom. F is pretty big over here. And let's do P, purple P. And let's say that P is also pretty big over here. So P is actually something like this. It's always positive. That's P, the true distribution of X. And here, where is most of the mass of this expected, or where's most of this integral happening? Where's the action? It's the same thing. I'm just writing the same thing here. F of X, P of X, little x. Well, it's all the action is over here, right? Because the product of F of X and P of X is large in magnitude. It's large in magnitude in this region. And it's not doing much over here. It's very small. So, if for some reason we were, crazy, and the only, or maybe we weren't crazy, but maybe for some reason the constraints are such that the only distribution that we can sample from, we can't sample from the true P, and the only distribution that, or distributions that we can sample from look something like this. Maybe draw it more like that P over here. And so for some reason it's very, very difficult. That should be positive everywhere. Sorry. It's kind of dropped below 0 there. For some reason it's very difficult to get samples from over here. Well, then we would be in very bad shape, because our Q, we're getting all these samples, and we're really not getting a representative estimate of the expectation, because all the action is over here. So the moral of the story is that you want to choose a good, you want to choose a Q where you want to choose Q to be large, where, so moral, let's put this, moral of the story, choose Q large where the magnitude of f of x and p of x times p of x, so the absolute value of f of x times p of x is large. And the situation which is very bad is when Q is much smaller than this absolute value. I mean, this could have been flipped the other way. F could have been, flipped the other way, and because f can be positive or negative, and this would still account for most of the action in the integral. So you want to choose Q large where this is small, and you want to avoid the situation where Q is small and this product is very large. So that one was good. This one is bad. And one problem with this is that not only is it bad, but you might not know that it's bad. It might be very difficult to assess how good of a quality your estimator is, because you're getting all these samples over here, And when you evaluate the the variance of your the sort of, if you try to estimate the variance using cross validation or whatever, then it might look pretty decent. It might not look bad, using Bootstrap or some sort of method for empirically evaluating the variance. Then it might not look too bad. But in fact, it's horrible. It's awful. And you might not know that. So that's one sort of gotcha that can happen with sampling methods. Something to keep an eye out for.